Okay, looking at the next lesson here and at 524, what does a log graph look like? So in this lesson, we're going to investigate graphs of logs, right? And since log of x is the parent function, right, the base is 10, this is important that we can visualize transformations as well as sketch the graphs. So let's start here and explore. So we need to graph the log of x, but we don't have a calculator. So write the equivalent form of log in an exponential. So if we have y equals log of x, right, and we're writing this in exponential form, this is a base of 10, so 10 to the y equals x, right? So then B says logarithms and exponents. How are they related? Okay, what is the inverse of this equation, right? So these are inverses, right? So if we go back to how we were taught inverses, y equals 10 to the x, we switch x and y, right, which you can see we're now look like this equation, right? And then we solve for y. Well, how do we solve, right? We take it, we log both sides, right? So we log x, we log this, right? The y comes to the front. And then we know log base 10 of 10 is 1, so this goes away, right? And we now have y equals log of x, which is back to what we are. So these are inverses, right? So log is the inverse of 10 to the x, right? So it now says make a table. So if we made an xy table, right, t table, whatever you're called there, right, we can do the exponential pretty easy, like anything to the 0 power is 1. 1 would be 10. 2 obviously would be 100. Okay, and then obviously if we went -1, it'd be 1 over 10, right? We get that exponential, right? And so then what do we know about inverses? Their x and y's are switched, or their domains or range are switched, right? So you know, this graph we know looks similar to this, right? And our domain is all real numbers, and then our range is 0 to infinity. So our domain is all reals, and our range is 0 to infinity. Okay, doesn't touch 0. But then if we look at our log function, right? So this is 10 to the x, right? This is our log, right? If we switch these, so this is 1, 0, 10, 1, 102, 1/10, -1, right? So now we're able to have an idea of what this graph looks like, right? So if we're doing this, right, we're at 1, 0, we're at 10, 1, so we're barely going up here, but at 1/10, so right here we're at like -1, so this graph is going to look something like this, right? And so our domain and range are switched, right? Our domain would be 0 to infinity, and then our range would be all real numbers, right? Because this is going to continue to go up. It's just very, very slow. Okay, so now we can explain what the graph looks like. We can explain where that locator point is at 1, 0, just like in exponentials, it's at 0, 1, right? And we can see that, an inverse graph is flipped about the line y equals x. So if I flip that graph over, or this graph over, we can see that they're inverses. Okay, 94. Graphing logarithmic functions with different bases. So let's just look here, and I'm going to use Desmos to do this, but let's look at like log base 2, like what happened, like what's the difference here? So in Desmos, right, let's go functions, right, and then we'll find log, right, and we do log of x. So we can see there's that graph that we just graphed, very similar, right? So now let's see what happens when we change the base. So log base 2 of x. So we can see like that base as an exponential, it grows, right? So when it's a log, it's an inverse. It actually, the smaller that base, the more it goes up, right? So what happens, coach, with like the next one says natural log. Well, we know natural log's base is e, so it's like 2 point something, right? So you can see it's there in the middle. So like if we wanted to get closer to that regular log, we would have to get a base closer to 10. So let's say we had like a base of 9 maybe, or let's just do 8. You can see that's going to put us closer to that base of 10, right? And so that gives you an idea of like what's happening. It's more of like a stretch compress, deal there. Okay, transformations, right? So these are going to be very similar to what we've seen in the past. So let's look at this first one here. So let's go. This was a log base of 3. Oh, it's going to make me re-put the function in. That's okay. We can do that. So let's re-put the function in. So we have a log base of 3, right? And then to the x, right? But what happens if we put a 5 in front of it? Again, still a vertical stretch, right? So we can kind of see there, no 5, vertical stretch. Okay? Let's look at the next one, right? So we have that small base, right? So that's going to make it grow big, like larger, right? And then we have -2. So let's see what happens there. All right, so we have a log base of 0.5 to the x, right? Oh, look at that. So 0.5 kind of goes back to like growth and decay, right? So exponential bigger than 1's growth, between 0 and 1's decay. So that kind of changes that, right? So now let's see what happens then. So, but still that locator point is still 1, 0. And then let's go -2. Right, so what we can see now is there should be, it takes that locator point from 1, 0 to 1, -2. If I can get it, there we go. So hopefully you can see that, right? Okay, so same thing here. We should start to see this pattern, the same transformation pattern, right? Where is this going to move this? Right 3. So it's going to take that locator point, move it to the right 3. What's it going to do to this log? It's going to vertically flip it, right? What's it going to do here? It's going to move it left 4, up 1, right? So it's the same transformation rules that we've seen with any function, okay? And this one, this is a try. Like I would love for you to try this on your own and see if you could figure this out. But it's using graph paper to find a distance. So being able to get your y value of 20 and then figuring out how far it actually was when you know each square is a quarter of an inch. So it's a really cool, idea of like, okay, I got this value, now can I find distance based on what I know using a scale. So this is 5.2.4.